Hi, I'm Sterling Baird. I direct the training programs at the Acceleration Consortium, an organization dedicated to accelerating scientific discovery through the use of AI and automation. And I'm really excited that you're either considering taking one of these courses or you're already enrolled and registered. And I'd like to go through some of the details of these. So first, I'll start off with this kind of analogy. How many of you have ever been off of a high dive before? If it was your first time, your body will probably have some pretty severe responses to this. You start looking over the edge, and your body's telling you, don't go any further, don't go closer to the edge. And we know that we can do this safely, but a lot of times getting into something like AI and automation in the sciences can feel very daunting. And so one of the main purposes of these courses is to create a situation that's a little bit more like jumping off the side of a pool or jumping on a smaller diving board and helping you to ramp up to something like a high dive with a much riskier and higher impact research project. So in this course, we'll be going over three main things. First is an introduction to self-driving laboratories in general, these autonomous scientific laboratories, and going over the course itself, trying to provide some motivation behind choices in the course, and then also going through course navigation just to help you get up to speed on that. So first, let's talk about self-driving laboratories and how we can use these for faster materials discovery. Here are some examples from years past. So sometimes we'll see these lateral-based arms that are picking up vials, moving them to different stations, doing liquid dispensing. We'll also see some solutions that are microfluidics-based, so flow-based systems with inline characterization. Also get into 6-axis arms, moving things in a generalized 3D space from one point to another. We'll also see some different flow chemistry setups with lots of tubes, and we'll also get into this sort of mobile laboratory chemist trying to mimic what a normal laboratory environment would look like. Taking this even one more step further, in the UK, here we have the system where a dual-armed robot is uncapping vials, which will then be transferred to this mobile robot, a mobile manipulator, the 6-axis arm on wheels, pulls it in and transfers those samples over to a characterization machine, in this case an X-ray diffraction machine, and it will navigate. Here we see a sped up video of it making its way over to the XRD. Once we're there, we have the task of opening the doors, so we calibrate our position and open those doors. And let's not forget that we have a second step, which is to actually load the samples. So we move a little bit closer, calibrate against this positioning block. Grab our samples. Place them inside using this hard-coded path based on this kind of local reference frame. And now we need to close the doors. So calibrate one more time, slowly grab those doors and move them to the closed position, at which point we're ready to go, starting the automated characterization sequence, and then we'll grab the samples when it's done. Now I think that this kind of workflow that we see can be daunting for a lot of people. The question that might naturally arise is, how many months or years did this take to set up? Now, I pulled the main PI aside after a talk and asked this, and the answer was that this took an entire PhD student's time at the university. Now, keep in mind, this was in the UK, so this was around 3 years, and one of those years was COVID. When asked how long it would take to replicate this setup in a separate laboratory, the answer was around half the time, maybe a bit less. And so going back to that high dive analogy, what can we do, what steps can we take to reduce the frustration and the kind of ambiguity of reaching these highly automated workflows. And so going a little bit more into what a self-driving lab actually is, this is something that closes the loop of scientific discovery. So we have this process where we initialize some search campaign, we set our goals, and the parameters will decide to change. We design or decide what we're going to make, which we then make and characterize, and we do this iteratively until we reach some stopping condition. For example, you run out of money on your grant, or you graduate, or you hit whatever performance metric you were hoping to achieve. And a self-driving laboratory has these two key pieces that I keep bringing up: AI and automation, where the purpose of automation is to minimize the burden of the experiments. So these would be things like reducing tedious steps, increasing your reliability and the replicability, and increasing your speed and throughput. On the other hand, AI is all about maximizing the value of individual experiments. So how can you reduce the total required number of experiments? How can you choose experiments intelligently, ones that give you the best information from them? And then we also get into predicting properties and quantifying the uncertainty of those predictions. Fully self-driving laboratories are ones that can perform many iterations without human intervention. So in this scale of AI and automation, we'll go from completely manual and then human ideation all the way up to these full workflows that are running over multiple iterations. So this kind of takes from what you might see from the autonomy levels of self-driving cars applied more in a scientific laboratory. And really, kind of in the near term and where we're aiming for is being able to, within an experimental campaign or a materials discovery campaign, run multiple iterations without human input, or at least not needing human input. We can still incorporate human domain knowledge and humans at various steps where it makes sense, and then also having our decision making coming into play there. We can also take a slightly different look at this. So self-driving labs automate and connect hardware and software across these different pieces. So if we were to take different categories: synthesis, characterization, transfer of samples, experiment planning, we can, on a case-by-case basis, say, okay, this setup is a fully manual setup. So we'll mark that with the X emoji. And then we can go all the way up to fully autonomous, where we are automating the synthesis, the characterization, the transfer of samples between everything, as well as our orchestration and our decision making there, where the goal naturally is to get higher levels of autonomy, with the idea that this will reduce the burden of experiments and increase the value of each experiment that we do. Now, a self-driving laboratory is a sort of monstrosity of connected tools. So we have some overall orchestrator. Usually this will be something based in Python that is interacting with hardware. So we have the software hardware communication interface. We're trying to make decisions. We're logging data somewhere. We're running things in a loop. And then we're also trying to access external resources at various times. Self-driving laboratories, going a little bit more into that decision-making process, will often use state-of-the-art algorithms to select the next experiment to run. So every materials optimization task is something of the form of find the set of parameters X that minimizes some target property or set of properties Y. And what we'll see time and time again is that when we use tools like Bayesian optimization, that we get a really stark performance increase relative to our more traditional design of experiments things. So you can see here, starting around iteration 12, I think it is, very quickly Bayesian optimization starts to find that true minimum in the space, that optimized property, much faster than things like random search or grid search, or even some quasi-random methods. Maybe you've heard of Latin hypercube sampling. And we see the same trend for other tasks. You could take one in material science, find a set of composition and processing parameters that maximizes the strength of an alloy, or something in drug discovery, find a better HIV drug that has this maximum binding affinity. And researchers have used a self-driving lab. This one was actually distributed across the world with 3 different laboratories, and they used Bayesian optimization under the hood to discover the world's brightest molecule in a very accelerated time frame. So that goes over a little bit about self-driving laboratories in general. Next, we'll talk about these courses and how these will help you to gain the skills and learn the terminology and the concepts necessary to both build these solutions yourself and work in interdisciplinary teams for it. Designing and building a self-driving laboratory can be a little bit like playing Mario Kart. You have a character and a cart that you choose, and based on that configuration, you end up with a set of skills or characteristics, speed, acceleration, how well this handles. And we end up with this question, would you rather hire Mario, Baby Peach, or Bowser, at least neglecting child labor laws and anger management issues? We take a look at Mario, and he's overall just well-rounded. Baby Peach, and she has great handling, but not as much speed, really high acceleration. And then, you see something with Bowser, really high speed, poor acceleration, poor handling, things like that. Now, this question comes from the idea of, how do you distribute skills here? And each researcher that is in the self-driving laboratory space or is looking to get into it comes with some set of skills. You might take a classically trained domain scientist in chemistry or physics or material science, somebody without classical training in robotics, maybe some familiarity with the computational sciences, some with data science, but again, low classical training on software development or engineering. Now, someone or something needs to glue these cross-disciplinary skill sets. When we take the extreme case where we have a chemist and a roboticist all coming together, in some cases it's almost like speaking different languages under the pretense or guise that everyone's speaking English or whatever the language is. And oftentimes this can turn into a bad joke, something that starts off like a chemist, roboticist, and data scientist walk into a bar. And again, in this extreme case, we can kind of think of it like a dot product, that the collaborative success is the dot product of these individual skill sets. And if we don't have some of that cross-domain conceptual understanding of the terminology and seeing how it fits into the bigger picture, we can get a fairly low sort of dot product magnitude at the end. Let's try to hammer this point home with a specific example. So we'll take an aryl halide, which many chemists would be familiar with, and then this idea of a posterior distribution, which data scientists, especially those familiar with Bayesian methods, would be very familiar with. So first we can look at a definition. An aryl halide is an aromatic compound where one or more hydrogen atoms in the aromatic ring are replaced by halogen atoms. At this point, probably still not really understood well by cross-domain experts. We could take a look at the formula with a smile string. Again, probably not the most useful. We could visualize it, and maybe that helps a little bit, but there's some question as to what this visualization actually represents. We take the cross-domain example, a data scientist, and we say the posterior distribution is a conditional probability that updates the prior probability with information from the likelihood via Bayes' rule. Again, a chemist that's looking at this would likely be utterly confused without some classical training in that aspect. We could take a look at, again, a formula, and this is Bayes' theorem or Bayes' rule. But again, maybe not all that much understanding. We could take a look at a visualization that shows how we move from a prior distribution to a posterior distribution. But really what we need is finding ways that will really compute and translate well for our cross-domain experts. So we could have a chemical formula, maybe show a different kind of visualization, and especially add something like a legend there. Same thing for labeling our visualization, looking at a prior, a likelihood, a posterior distribution, and showing how that relates to our formula from before. And maybe going a little bit further, talking about what our objective function value is, our measured value, and our observation location. And so really digging in, trying to figure out what we can do to help our cross-domain experts understand where we're coming from and help us to understand where they're coming from. And this is an opportunity for the Acceleration Consortium's microcourses to help in providing this glue for autonomous laboratories. So we have 5 courses in this certificate. Each course has a micro-credential, sort of verifiable record of completion of a course, and we go from a Hello World course where you design and build a small self-driving lab from scratch. This is launched and active, and then deeper dives into data science, robotics, and software development, which many of the chemists and material scientists will not have classical training in these. And so you'll look at optimization and databases here. You'll be controlling robots and orchestrating different workflows within the robotics course, and then you'll learn best practices that will help maximize throughput and reduce frustration in the software development course. These culminate in a design project where you take what was learned in the 4 previous courses, which are asynchronous, each around 25 hours, depending on skill levels and prior experience, and you take those and put it together in a project proposal that's completed in person at the AC training lab. So 4 asynchronous courses, 1 kind of culminating one, and we have these prerequisites. So beginner Python programming experience is assumed. There's a small hardware kit necessary for the first course, and then there's some wireless requirements for that I'll go into more detail on later. So let's talk minimal working examples. When we take the simplest case of a self-driving lab that is still somewhat interesting, we get color matching. So we have these 3 previous ones we talked about. Find the set of parameters X that minimizes the target property Y. We had that for aluminum alloys and HIV drugs. We have a similar task, find the set of red, green, and blue LED power levels that minimizes the distance between measured and target color. So that looks like this. We have our dimmable red, green, blue LEDs, some microcontroller. Depending on the power of these, we get a spectrum of light, which we can measure at discrete values using a light sensor. We arbitrarily set, okay, we want to match this, this is our target color, the one we want to match. And then we take the difference between what we've set as our target and what we're currently measuring. And the question becomes, what method can I use to reach the target? We run this optimization in a loop and until we converge on our matched colors as close as we can. And this is a very low footprint, easy to set up, and fairly low cost demo that can be used for a self-driving lab. And the components required in this kit are fairly minimal. So we have a microcontroller in green here. This is a Pico wireless microcontroller. We have our light sensor over here. And then this purple board here is just a convenient kind of breadboard-like item that comes with a red, green, and blue LED built in, and also these nice Grove connectors, which makes it easy to connect from the microcontroller to the light sensor. We have some mounting wire just to make sure the sensor goes at the right orientation to the LED, and then we also have just a USB cable and wall charger, since this can also be set up standalone without a computer. So here's what it looks like assembled. We have the mounting wire that fixtures the light sensor relative to the LED. The microcontroller goes on this kind of breadboard-like base. We have the connector between the light sensor and the board. And all of this very conveniently can be purchased with a single one-click DigiKey shopping cart. And so that all goes through DigiKey, one of the major electronic suppliers in the world. The estimated time frame for completing this, each of these courses, is about 25 hours, and this assumes some beginner Python. And that might mean you've taken a Python course recently that lasted around 20 to 30 hours. And so if you're coming in without any programming experience or without Python experience, then you might take a little closer to 50 hours without that. There is a Python refresher assignment at the beginning. This goes through imports and modules and packages, different data concepts, logical concepts, and operations. And so this can kind of give you an idea of what will be covered in, or kind of assumed or expected that you know in the later courses. There are also some additional resources for learning Python. You can navigate to this AC Bayesian Optimization Hackathon website with the resources. There are some listed there. GitHub Copilot chat, and then large language models in general can be really useful for learning coding in recent, within the last year or two. And then also just kind of plain old Google searches and Stack Overflow are great resources as well. And you'll hear a lot of people say, learn Python with a project that you care about. If you're passionate about self-driving laboratories, materials discovery, then this is a great excuse almost to learn programming language if you haven't already. And this course requires a 2.4 gigahertz WPA2 personal Wi-Fi network. That may not mean a whole lot, but what this translates to is that you need to be able to access a network that only has a Wi-Fi name and password, no username. So things like Eduroam or a lot of these built-in university networks are not compatible with that. They're not these kind of Internet of Things style Wi-Fi networks. The 2.4 gigahertz refers to the band. The complement to that is 5G. So we're looking at 2.4 gigahertz instead of 5 gigahertz for that. And so lower data throughput, but also less expensive to set up. And if you're using a hotspot on your phone, for example, you'll see something that's like maximize compatibility. And when you check that, it changes it from a 5G band to a 2.4 gigahertz band. Same thing with Android. You might see something like extend compatibility. If you don't have a hotspot or a network like this that you can use, you can get some standalone home internet solutions. And so this could be like a SIM-enabled device, or it could be a home internet. That will depend on which router you have. Then we also have mobile hotspots, which will mostly depend on which country you're in. And then eventually, Eduroam support is anticipated, but it's not yet supported with the Pico Wireless. This is a software limitation, not so much a hardware limitation on that. Each of the courses have 3 parts: a tutorial, a quiz, and an assignment. So the tutorials are hands-on. You'll have some different videos or other resources that you'll read, and you'll have some kind of practical example that you can implement, maybe on your microcontroller, maybe in a Jupyter notebook with Python. And then you'll take what you learned from there to complete these knowledge checks or quizzes. All the information in here, or all the answers, should be available based on the resources listed in the tutorial. The assignment is a somewhat more complex version of what was covered in the tutorial, and I'll give a specific example later. But here you'll have starter code that you'll fill out, and then we'll run automated tests to do the auto grading. And as you go through these courses, you'll gain exposure to the same tools used by software developers. So for example, auto grading happens via GitHub Actions and PyTest. So we run these tests as part of what's called a continuous integration pipeline. And so this allows you to automate the setup and delivery and testing of code to make sure things are working properly, to make sure that whoever's using it at the end can use it with the most recent updates as well. Assignments themselves are actually just GitHub repositories. So that means you can use code spaces, and a lot of the assignments are based on, there's instructions for using GitHub code spaces. That gives you this Python environment you can work with that is just in an online browser, but you can also just as easily download the code locally with a process called cloning and use that in Visual Studio Code or GitHub Desktop. When you have that, you'll get a URL for your assignment. It'll be listed as private, and you can use any of the GitHub GitHub buttons native there to open it. So far, we've talked a lot about the motivation behind learning these concepts. We've also covered very specific choices in the organization of the course. But what we haven't talked about is the actual content. What are the concepts that will be learned? What are the tools that will be used in this first Hello World course? So in the orientation module, this is just about getting you acclimated to having a GitHub classroom assignment and running the auto grading, committing and pushing your changes for your assignment. Then with the first module, this is where you'll really get this demo set up in a kind of batteries included sense before you try to start building it from scratch. And this gives you kind of an early win to see what you'll be building by the end of it. So you'll order the parts, so make sure you have all the prerequisites. In step 2, you're setting up the firmware on the microcontroller. In step 3, you're assembling all of the hardware. And then in 4, you're taking a look at running an optimization of the color matching experiment using Google Colab and a Jupyter notebook. And we'll take a look at comparing Bayesian optimization versus some traditional design experiment methods. In the second module, this covers just a very simple control of the microcontroller itself. So we go from microcontroller controlling the RGB LED and then reading the sensor data without any of the other aspects. Just a very small example there. In module 3, we get into this concept of Bayesian optimization and looking at comparisons between traditional design of experiment methods and then actually implementing the Bayesian optimization using, in this case, the ACE platform by Meta, and you could also use a variety of other algorithms, but this is the specific tool we use here. In module 4, this is where we really start talking about hardware and software communication. In this case, we're using MQTT, which is one of the de facto standards in Internet of Things style communication. And this is a tool where you have a central broker, and then you have these different clients that will subscribe to certain topics on that broker. So if we just take an example of temperature, we have on our microcontroller a built-in temperature sensor, and we will publish the temperature to a topic called temp. And then on the Python side, we can subscribe to the temp topic and then receive that data that's published by the PicoW microcontroller and receive that. So we have this cross communication, and we now have physical hardware interacting with software over Wi-Fi using a secure encrypted service. In this case, we use HiveMQ Cloud that hosts an MQTT broker for us. In module 5, we take a look at data. Where do we put the data, and how do we keep that in a persistent format? Our device communication was really about real-time communication, but not so much about persistent storage. So with this one, we'll use MongoDB, a very popular and well-accepted database. You have other ones like SQL, PostgreSQL, that are more relational databases. You could also host things locally, just in an Excel file or CSV file. In this case, we're looking at some of that sensor data and figuring out how to pass the sensor data and the original commands that we had to the database. Module 6, this last module, is where it gets both exciting and pretty complex. Here we connect the pieces from all the previous modules to get a fully closed loop optimization for color matching. We have our Bayesian optimizer using the ACE platform, which is running in a Python kernel. We have our HiveMQ Cloud MTT broker that is passing messages back and forth between our microcontroller, sending commands to the microcontroller, and then receiving sensor data back to our Bayesian optimizer. And we're logging data directly from our microcontroller that's running the actual experiments to a MongoDB database. And this will likely be the most rewarding and also the most challenging module of the course, where by the end of it, you will have built from scratch a minimal working example for a self-driving lab. I want to talk a little bit about standardization, not just as this philosophical piece, but really that we'll start facing significant challenges due to an absence of standard choices and tools. Now, I'll preface this with the idea that the tools chosen for this course are just one example of a set of tools, and the way this is framed, they're really quite interchangeable and swappable. I mentioned a few of them, like the choice of MongoDB for hosting the data versus a relational database, going from documents to relational databases. Same thing for the optimization platforms being used, the communication protocols. And I want to talk a little bit about an experience I had many years ago. One of the best courses, in fact, my favorite course that I've ever taken, is called Theory of Predictive Modeling. And in this course, I'm sitting here in this big lecture hall, and during one of the orientations, the professor says, for our assignments, you can use any programming language that you want. However, all of the examples will be done in Python, and the TAs will be equipped to help you also in Python. Now, coming from a physics background, I really enjoyed using Mathematica, and here I was thinking, you know what? I'm going to try to complete this whole course using Mathematica as the programming language. And it was really fun, and I used it. But what that meant is that I was unable to receive help from the TAs and the professors except on more of a high level conceptual level, and it also meant that I couldn't help others in the class. And so there was this break due to the choice of standards. While it was really fun and exciting to use, in terms of the amount of work and the streamlined efforts, it may have made more sense to have picked up Python at that time. The example I just gave was really specific to programming languages, and Python is actually the standard and probably the most widely used programming language within the physical sciences. This also applies to the other tools and the suite of tools and different practices that will be used in building this self-driving lab. We have Tim Peters here, author of The Zen of Python. I encourage you to check that out if you're not familiar with it. And he says, a universal convention supplies all of maintainability, clarity, consistency, and a foundation for good programming. And I'll add other types of habits too. He says, what it doesn't do is insist that you follow it against your will. That's Python. And so standardization is not meant to be something that you follow against your will. You make careful choices and considerations about what tools make the most sense for your workflows, and comparing that against what's widely used and accepted by others in the community. I'd like to point out 2 resources that you can use to help minimize the redundancy and maximize your alignment within the community as you're thinking about conceptually how to set up these self-driving labs and which specific tools to use. The first is called Awesome Self-Driving Labs. You can find this with an easy Google search. This is a curated list of resources related to SDLs. And then we have so far a decent number of contributors, and this goes over review papers that are available, specific implementations of self-driving labs, and lists of tools that are software-based ones and hardware-based ones. Second, we have the Accelerated Discovery Discourse Forum. Now, this is a more persistent and long-term format of discussion that's open to the community. It's a place to discuss, brainstorm, and get help on SDL topics. So you can see, for example, powder dispensing, syringe pumps, just general recommendations to get into the self-driving lab space. So I highly encourage you to check out those 2 resources. So far, we've talked about self-driving laboratories, trying to give some motivation and context for that, and then Also, we dove into the course overview, some specific choices in how it's set up and designed, and why you would even want to take this course. In this next section, I'm going to talk about navigating the course itself to try to make the experience a little bit smoother. So first, everything begins at the readthedocs site. So this is AC Microcourses, or ac-microcourses.readthedocs.io. Here we have the Read the Docs page. This is all hosted in GitHub through a GitHub repository called AC Microcourses. I'd encourage you to star this repository, which will make this project easier to find, and it'll help spread the word and also help to justify future work on these course developments. On the homepage, we have some header buttons at the top. You can take a look at the source repository. You also have some other things like showing the source, downloading a file, changing the light versus dark mode, and going full screen. In this table here, we can take a look at the course pages for each course. Here we have the Overview tab with information about the prerequisites, learning outcomes, as well as specifics about each module within the course. And you can see this for the other courses as well. Next, we have our primary navigation sidebar to the left. You can use this to quickly jump to different pieces of content, for example, the overview that we're just at. We also have these 3 horizontal lines that you can use to toggle it, and a search bar to search through the entire Read the Docs site. We also have a navigation bar on the right, a secondary bar to navigate within a page. If we scroll down a little bit, we'll find the table of contents and this tip that we can use the left and right arrow keys to navigate. So we'll tap the right arrow key, get to the landing page. One more time, we'll get back to the course overview. Here we'll scroll to the bottom and get into our first content piece, which is the orientation. You'll notice the registration link. When you're ready, go ahead and click that. This will take you to the School of Continuing Studies website where you can select a section and click Enroll Now. From here, you'll just do a typical checkout process, but you will need an account through the School of Continuing Studies. So you'll put in an email and you will fill out some information. There's a lot of information that's requested here. The ones that are required are name, date of birth, email, phone number, address, and whether or not you want to be added to the mailing list. And this allows a student ID to be created for you and for you to be awarded an official School of Continuing Studies micro-credential after you complete the course. From here, you check out as normal with a credit card and review the policies of taking the course. Once you've reviewed that, check the box and you'll continue the checkout. This will take you to a confirmation page. Which will have a receipt that you'll also get by email. So if we look into that email, you'll see a PDF copy of that receipt, as well as information like your student number and any other kind of policies that were mentioned before. It will take about 24 to 48 hours to actually get access to the course. And what I mean by that is the quizzes and the assignments for the course. While you're waiting, you can start with that orientation module. You won't be able to access all of the links there, but quite a few of them. And then you can also get started on the Run the Demo or the Module 1 tutorial. Once you do get the email, it'll look like this. You have your Quercus access letter, and you'll go to q.utoronto.ca, and you're given your credentials in the email itself, and you'll use that to log in. Here's what that landing page looks like for logging in once you've entered your information. Next, we'll come to the Quercus dashboard. If you're familiar with Canvas, the learning management system, Quercus is University of Toronto's instance of Canvas. And you'll notice towards the bottom there, we have the section of the course listed, in this case, Spring, Summer 2024. We'll use that a little bit later on. Here, we'll also see that same Spring Summer 2024 used. This will help us when we're accessing the quizzes from the Read the Docs site. We can go back to the course content. Here is just the regular Read the Docs site, just in dark mode. And then here we have the syllabus with course logistics and other policies. You'll also find some forms here, like having your final grade and requesting the micro-credential, a learner equity survey that you can fill out, as well as a final course evaluation. If we head back, we also have grades that we can check. So as you continue through these different assignments, you can look at individual grades and your final grade. If you use the checkbox at the top right, then you can also take a look at your totals for the course. And so there are 125 possible points in this one, and you need a 70% average to be considered passing. And we also have along the left, you can find the syllabus, grades, and quiz there as well. Once again, there are a few ways we can navigate the site to get back to our orientation module. Of course, we have our exploring the overview that we can do with the buttons or the forward and back. We have our begin course content. We can also just jump straight there with the navigation sidebar. And once you've registered and gained access, you'll be able to actually access your Quercus content. If we take a look here, this shows that you'll need to know which section you're enrolled in so that you can select the appropriate tab for the quizzes and assignments. If you select one for a different section than what you're enrolled in, it'll show access denied, so just switch to a different one and you'll find that. Here we can click take a quiz, and this first one will ask for your GitHub username. And it will also ask for your student identifier, which will appear once and only once when you first accept an assignment and select the identifier. Scrolling down a little bit more, we have some more information about GitHub accounts and then this GitHub starter tutorial. At the beginning, we'll have different walkthroughs that can help with getting oriented. The goal is not to teach you about GitHub Classroom, but to use it as a tool. And then here we have this other walkthrough for our first intro to GitHub Classroom assignment. Once you've completed that, you'll self-report your auto-graded score from GitHub into here, as well as provide some basic feedback, how long it took you, and any other feedback or suggestions that you have. You can always access your GitHub repositories by clicking on that assignment link again, or you could go to the ACC Hello World GitHub organization to look at your repositories. Going a little bit further, we have a Python refresher assignment that you can do. This is ungraded, as well as a link to the syllabus. With Module 1, this is where we actually need our hardware kit and our wireless network. You can order the required components using this link, make sure that you're getting the right power adapter for your country. And there are also some recommendations on getting the right Wi-Fi network to be able to do the course. In this step, you'll run through this video tutorial to actually assemble the hardware and run a batteries included version of the demo. Now, this first module is sort of a sneak peek at what you'll build from scratch in all of the other modules and integrate together. The course assumes the use of Thonny, this very easy to use integrated development environment, or IDE, for running MicroPython and installing it onto the Pico wireless microcontroller. But you may also prefer to use the MicroPico extension in VS Code for this instead. Next, we have a quiz and an assignment. In this particular quiz, we have a word bank. You might need to zoom out a little bit, and you'll grab items from the word bank. In this case, the hosted platform used for MQTT communication is HiveMQ. Once you're ready, you hit submit, at which point auto grading will start. And this is just auto grading on the Quarkus side, not for your actual coding assignments. You'll get to see what you got correct, and you have an unlimited number of attempts on this. There's also a 5-minute partial walkthrough of doing the entire run the demo module. If you get stuck, you can refer to the build instructions manuscript, which is linked, as well as the GitHub discussions for AC Microcourses, which I'll go into some more detail later. In particular, this is where those discussions are. There's a Hello World category, and here you can get some help on the different modules. Finally, we'll go to our assignment, which has a link back to our GitHub Classroom assignment, and we'll follow the instructions there to figure out what our auto-graded score for the Python code is, and then enter that score into this quiz. We can also put in the number of hours that were spent on the module and any feedback that you'd like to include. And then you follow this same process for each of the other modules up to module 6. While this is a self-directed and asynchronous course, you might get stuck and need some clarification on something. Again, you can use this Get Help button, which should be included on the landing page for each course. This will go directly to your Hello World category in this case, and you can click the New Discussion button in green to open a new discussion. But before you do that, be sure to look through existing ones in case your question is already covered. You also have these labels that can be applied for specific modules and make it a little bit easier. Here's an example of a really great discussion and question. So notice here at the top, talks about what the kind of a summary of the issue, and then also specific code outputs are being included, as well as this kind of nicely formatted error. Also notice that this person has included a link to their actual file on their GitHub assignment. Now this is a private link, only people with access to that repository can get the link, but it makes it much easier for the maintainers to help with debugging. When you have an auto-grading workflow run, it also helps to be able to have a link to that just to go directly and see this fully reproducible example of the auto-grading happen. And you could also include the full output from PyTest, for example, either in plain text or with that file attachment. You might find something that is wrong or needs to be improved. In this case, you can use one of those header buttons to open a new issue on each page, and you'll enter a title and a description for your issue. You can take a look at the contributing guidelines, which gives an idea of how things can be structured. For really simple things, feel free to just put in a question or an issue and include any relevant information. But for more involved contributions, then the contributing guide can help with that. Even better, if you have specific ideas on how to fix a bug or improve the documentation, you can suggest an edit via this button towards the top, and you'll be able to do something called a GitHub pull request. First, you need to make a linked copy of the repository that's called a fork, and you'll be able to do some simple edits using the GitHub editor UI. And so this file in particular is in Markdown format. You can look up GitHub flavored Markdown. You'll also get some nice kind of formatting buttons in the header towards the top usually. So you can make your edits, and then you'll scroll back up to the top when you're done and press commit changes. You can add a message clarifying what you changed. Then you click propose changes, which allows you to review your changes before clicking create pull request. And then here you'll add a title, a description, and then click this button, create pull request. At this point, it's now available for any maintainers to see, and they can look through the edits you've made, and you can work with them to be able to merge those into the main code base. So far, we've covered self-driving laboratories in general, what they are, what kind of impact they can have on science, and especially accelerated scientific discovery. Next, we talked about these courses and the Hello World course in particular. Why would you want to take this course? Things like building up common vocabulary and conceptual understanding. That's really important for working in these highly interdisciplinary teams. You'll also get hands-on experience with tools that are used in practice to build self-driving laboratories and figure out what the best practices are for this. Finally, we went through the logistics of how you'll navigate the course documentation, get registered for the course, submit assignments, how you can get some help if you get stuck, as well as how you can make contributions back to the project. I am very excited to have you participate in this course and have this as one step on your journey towards developing autonomous and scalable self-driving laboratories for discovery in the sciences. Thanks.